In the same chapter, we have one more instrument by name potentiometer. What is its use? First and foremost, it is used in measuring the EMF of a cell. It is used to compare EMFs of given two cells. It is even used to determine the internal resistance of a given cell. So there are three different areas you have to concentrate as far as this potentiometer that is concerned. What is its principle? First of all, potential gradient that remains constant. What do you mean by this potential gradient? That of course we can write it as dV by dx. That now must be constant here. In other words, you can even say, if E is EMF per unit length of the wire, that remains constant. So when you just take this potentiometer, it will be having a wire of length around 8 meter, 10 meter, 12 meter, like that. And in fact, we all know, more is the length of the potentiometer wire, more will be the sensitivity of that instrument, more will be the corresponding accuracy of that instrument. So that is one area you have to concentrate much on. Now the second point over here, when we consider this potentiometer circuit, you will be finding one circuit again is called as primary circuit. This primary circuit is going to have a cell of greater EMF, and secondary circuit, whatever we are finding here, that now will have a cell of EMF E1, which is to be determined there, and that again is going to be connected to high resistance, then to galvanometer, and that galvanometer is directly connected to the potentiometer wire. It can in fact slide over by means of a jockey. Now, if you just look at this is primary and this one is secondary, one point we should understand, voltmeter and potentiometer both are going to be used to determine EMF only, but potentiometer is preferred more. What is the reason? For that one theoretical aspect you have to remember. Potentiometer will never extract current from the cell connected in the secondary circuit. When potentiometer is not extracting current from the cell in the secondary, automatically the EMF of that cell can be determined with utmost accuracy here. So definitely potentiometer is much more accurate than a voltmeter. So this is one theoretical aspect one should remember. Come to the second one. What exactly are the different equations of potentiometer? I'll simply remind you. When we are taking up one cell connected here as of EMF E1, let us take the balance length here is L1. Then what I can write here? E1 by L1 will now be a constant. Suppose if I replace this one by another cell of EMF E2, and if I get the corresponding balancing length as L2, then I can rewrite the same equation this way, E2 by L2, that now becomes a constant again. So what exactly is the equation we can produce? E1 by L1 must be equal to E2 by L2. Then what would be the way of comparing the EMFs now? E1 by E2, which is the ratio of EMFs of two different cells, is equal to L1 by L2. We can directly write. L1 is balancing length when first cell is connected in the secondary circuit. L2 is balancing length when second cell is connected in the secondary circuit. Now the same experiment you can perform in a different way also, which gives a different other equation for us to determine the ratio of EMFs of two given cells. Just in the secondary circuit, we are connecting both the cells in series. For example, one is of EMF E1, one is of EMF E2. Both are now connected in series across the secondary circuit. After that, after connecting them like this, we have calculated the balancing length as L1. Then what to write over here as an equation? E1 plus E2 by L1 must be a constant. That is, potential gradient is constant, again we can write. Now, one out of the two cells, you reverse that one. That means what do you find here? One cell is connected regularly and other cell is reversed. If I write its EMF as E1, its EMF is to be written with a negative sign there. Thereby, what is the corresponding length, balancing length after connecting this one over here in the secondary circuit? Again you calculate the balancing length. Suppose the balancing length is L2 this time. Then what can we write? E1 minus E2 by L2 is going to be constant now. Now, if you equate these two, what is the ultimate outcome you can get? E1 plus E2 by E1 minus E2 will now be equal to L1 by L2. That only you can apply by taking componendo dividendo. You can write E1 by E2 is equal to L1 plus L2 by L1 minus L2. This is another formula by means of which you can compare the EMFs of two given cells using potentiometer. So, two different equations you have to remember. Applications on both the equations you will find, and particularly the second one is one of the very important concepts for you to remember. Now, in the same manner, how can we directly calculate the internal resistance of a given cell using a potentiometer? That time, of course, to the same cell, whatever we are connecting it here, the cell whatever is connected here, across that one we connect an external resistance R, and there is another key that is provided here. The remaining system will be as it is. You will not find any variation as far as the circuit that is concerned. But what we have to understand here is, when you put the key in, then the resistance also takes part in the circuit. When suppose key is plucked out, then only this cell that takes part in the circuit in the secondary as such. Therefore, what we do in this particular case is, without the application of external resistance, we just determine whatever the balance length that is observed as L1. So that means when E1 is connected across the secondary circuit, L1 is the balancing length, for example. That is, without the resistance it is L1. Now put the key in, then the circuit will have external resistance also connected in the system. Thereby, whatever the length, balancing length we are getting, that you take it as L2. That means without external resistance, balancing length is L1. With the external resistance also connected, the balancing length you take it as L2. Then what is the internal resistance of this circuit? That is the question. R is equal to L1 minus L2 by L2 into R. What is this formula out of it? You just check it. L1 is the balancing length when only the cell is connected in the secondary circuit without the external resistor. L2 is the balancing length when the resistance also is taking part in the circuit, that is the secondary circuit. And capital R stands for the external resistance what has been connected over here. Thereby, if you use this formula, you can directly get the internal resistance of the cell which is connected in the secondary circuit as such. So, potentiometer, whenever we want to take up, three major equations one has to remember for any entrance exam, that is including JEE. If you take E1 by E2 is equal to L1 by L2 is one equation, E1 by E2 is equal to L1 plus L2 by L1 minus L2 is another equation. Likewise, for internal resistance of the cell, it is L1 minus L2 by L2 into capital R. These are the three different equations one has to remember as far as potentiometer and its application that is concerned. Let me now remind you few cases where we directly apply the concept of Wheatstone bridge. When we have three resistances connected like this, one more resistance connected this way, another resistance is connected like this. Let us say this point as B and this point as A. Each resistance you take it as R. All the five are of the same magnitude. Now this circuit, if you look at carefully, it is an application of Wheatstone bridge. You can see this one as the first branch, this one the second one, this one the third, this one the fourth, and this one is the resistance which is in place of the galvanometer. And another important feature, whenever in a Wheatstone bridge, if all the four values of resistances are equal, same value will now be the resultant as well. Now here what you should understand, these two are in series, these two are in series, and this resistance does not carry any amount of current. So automatically we can understand when these two are in series, the value will be 2R. These two are in series, the value will be 2R. When both are now in parallel, the effective resistance in this case will now be equal to R like. So whenever we consider a Wheatstone bridge in this form, you directly can estimate that these two resistances are going to be in series, these two resistances are in series, and both are now going to be in parallel. That is the concept one should understand. Now the same Wheatstone bridge even can be drawn this way also. One more example I will just give you. This is the case of an equilateral triangle having all the three sides, three resistances like this. One more resistance is connected across these two, the centroid and this end, one more here, one more here. Even this resistance circuit, if you take this one as R, this one as R, this as R, this one, this one, this one, each one is R like. Then also you can see, barring this resistance, you will be finding a Wheatstone bridge. Suppose if they are different by any chance, R1, this is R2, this is R3, this is R4, this is R5, and this one is R6. Suppose if they are different, they are all same means directly we can understand like this. If they are different, then what must be the condition for us to identify that one? R1 by R2, that must be equal to R4 by R5. R1 by R2 must be equal to R4 by R5. By any chance if this is true, then you can understand no current that flows across R3. When no current that flows across R3, R1 and R2 are said to be in series, R4 and R5 are said to be in series, and both are in parallel as far as Wheatstone bridge that is concerned. That entire Wheatstone bridge is now parallel to the other one also, that is R6. So what we should understand here now, R1 and R2 are in series, then what would be the effective value? It is R1 plus R2. and R4 and R5 are in series, the effective value will be R4 and plus R5. They are now in series. Now when both are in parallel and parallel to R6, then how do we write that formula? 1 by effective resistance, that is equal to 1 by R1 plus R2 plus 1 by R4 plus R5 plus 1 by R6. This is the way we people used to take up the effective resistance in that circuit. So when resistance circuits are given, if the circuit is consisting of a Wheatstone bridge, calculating the effective resistance is going to be a very simple concept. But one should identify where exactly that Wheatstone bridge is located. If you can identify that one, automatically you can estimate what is going to be the effective resistance across that. But in some cases, that particular circuit looks like a Wheatstone bridge, but it will not be a Wheatstone bridge. That means it will not directly obey the condition for Wheatstone bridge, which is called the balancing condition for Wheatstone bridge. In such cases, one should apply Kirchhoff's laws and solve the circuit as such. So those problems also one should be careful enough, and those applications also one should be thorough enough. Then only the application of Kirchhoff's law can be worked out easily in the final examination as such.